Introduction. The edge of cosmic sight. What if everything we've ever seen, every star, every galaxy, every trace of light was only a fragment of something much grander, hidden beyond our reach? The observable universe, with its hundreds of billions of galaxies stretching across 93 billion light-years, already feels overwhelmingly vast. And yet, it might only be a small window into a far greater reality in cosmology. The term observable universe does not imply a boundary of existence, but rather a limit to what we can see, because the universe is only about 13.8 billion years old, and light travels at a finite speed. We can only observe regions from which light has had enough time to reach us since the beginning of time. This boundary is not physical. There are no walls. It's an invisible horizon drawn by time and the speed of light. But what lies beyond it? Beyond this cosmic curtain, mystery reigns. The laws of physics may continue, but space could be radically different. There might be more matter, more galaxies, or nothing at all. Perhaps there are regions governed by alternate physical constants or entirely new dimensions of reality. Could there be an infinite universe beyond the veil? Or is it finite, yet looped in a way our minds can barely comprehend? For centuries, humans have stared into the night sky with a sense of awe. But only recently have we begun to truly grasp the scale and nature of the cosmos. As our tools sharpen and our minds stretch further, we are left with new questions that reach far beyond our instruments' limits. The greatest of these may be what lies beyond the observable universe. In this audio journey, we will explore the best theories, speculations, and scientific frontiers surrounding that question. From inflation theory to multiverse hypotheses, cosmic topology to philosophical musings, we will gently drift through the ideas that attempt to illuminate the unfathomable. Prepare to leave behind the familiar. Let curiosity guide you to the edge of everything we know and far beyond it. Chapter 1. The Cosmic Horizon. Why we can't see further. There is a boundary to our vision of the cosmos, a limit not set by walls or borders, but by time itself. This boundary is called the cosmic horizon, and it defines the outermost edge of the observable universe. To understand why this boundary exists, we must look not outward, but backward through time, toward the beginning of everything. The universe is approximately 13.8 billion years old, and light, the fastest thing we know, has been traveling through it ever since. But because light takes time to move, and because the universe is so vast, we can only see objects whose light has had enough time to reach us. That creates a kind of sphere around Earth, the cosmic horizon. Anything farther away simply hasn't had time to send its light to us. It exists. Soar may exist, but remains invisible. Yet, this horizon isn't a static shell. Due to the expansion of the universe, the farthest things we see today emitted their light when they were much closer. Space has stretched so much that these ancient galaxies are now more than 46 billion light-years away. Even though their light has been traveling for only 13.8 billion years. This is why the observable universe spans a staggering 93 billion light-years in diameter. This concept challenges intuition. One might assume that older light means closer origins. But because the fabric of space itself expands, it carries galaxies farther from us as their light journeys through the void. The result is a universe in motion, where distances aren't fixed and where the horizon we observe is a shifting, expanding frontier. It's important to understand that this horizon does not define the full extent of the universe. Defines what we can see, not what exists. Most cosmologists agree that the universe likely extends far beyond this limit, perhaps infinitely. But those far-off regions lie forever beyond our reach, because no light from them can ever reach us, not now, not in the distant future. There is a poetic strangeness to this reality. In every direction we look, we see only part of the story. We live inside a bubble of visibility, centered around Earth, but not because of any special positions, simply because that's where we observe from. Every point in the universe has its own horizon, its own sphere of light and time. Imagine standing at the edge of an ancient ocean, knowing the world continues across its surface, but seeing nothing but the gray-blue limit of the sea. What it means to live at the edge of the observable universe. We gaze outward, not to the end of everything, but to the beginning of sight. The cosmic horizon is both a revelation and a mystery. It tells us how far we've come and how much we'll never see. It is the first step into the unknown, a gentle veil drawn by the passage of time and the dance of light. And as we begin this journey into what lies beyond, we carry with us the realization that the most profound truths may forever remain just out of view. Chapter 2: Cosmic Inflation and the Hidden Universe. To understand what might lie beyond the observable universe, we must first revisit the moment just after time itself began. Within the first fraction of a second following the Big Bang, the universe is believed to have undergone a breathtaking transformation, a brief yet violent expansion known as cosmic inflation. This event, though fleeting, holds the key to why there may be vast, unobservable regions of the cosmos that we can never reach. Inflation theory proposes that the universe expanded exponentially within a tiny fraction of a second, growing from a size smaller than an atom to something unimaginably large. During this burst, space itself stretched so fast that entire regions were flung beyond the reach of causal contact. The space between points increased faster than light could travel. Between them not in violation of physics, but because it was space itself expanding. This has profound implications. It suggests that the observable universe is only a minuscule patch on an enormously larger cosmic canvas. The inflationary process may have produced a universe that is not just bigger than we see, but potentially infinite. Everything outside our visible sphere is real, according to inflation, but so far away that its light has not and will not ever reach us. Furthermore, inflation helps explain why the universe appears so uniform across vast distances. The microwave background radiation, a faint glow from the early universe, shows remarkable consistency in temperature, even between regions that couldn't have communicated at light speed under normal expansion. But with inflation, those areas were once in close contact, then rapidly flung apart. It's as though a calm lake were stretched into an ocean in the blink of an eye. Some versions of inflation theory go even further, suggesting that inflation is not a one-time event, but an eternal process, one that creates countless pocket universes or bubble universes, each with its own laws of physics. Our universe would be just one among many, separated by vast gulfs of inflating space. We might live in a cosmic archipelago where other universes float beyond sight, forever isolated. These hidden realms are more than science fiction. They arise naturally from the equations of inflation and quantum field theory. They cannot yet be observed, but their possibility shapes modern cosmology. They raise haunting questions. Do other universes harbor stars, galaxies, or even life? Could some operate under entirely different physical laws? Or are they empty, dark, and quiet in infinite wilderness of cosmic silence? Inflation may have given birth to everything we know, but it also sowed the seeds of the unknowable. It stretches the edge of reality far beyond our grasp and leaves us with a quiet truth. We may never know the full scale of the universe. We are confined to our observable patch, like fish in a vast and expanding pond, aware of a shoreline we can never reach. But even in our cosmic solitude, we carry the marks of inflation in the sky. The faint whispers of its legacy are etched into the background radiation and the structure of galaxies. It speaks of a hidden universe, immense and mysterious, waiting just beyond the veil of light. Chapter 3: The Infinite Universe Hypothesis. As we peer deeper into the cosmos, the question naturally arises: is the universe infinite? Could it stretch on forever, with no edge, no boundary, no end. This idea, both elegant and overwhelming, lies at the heart of one of the most profound possibilities in cosmology, the infinite universe. Hypothesis. The notion of an infinite universe is not new. Philosophers and early astronomers pondered it long before the age of modern science. But today, this hypothesis finds grounding in our best cosmological models, supported by both theory and observation. Geometry of the universe evidence suggests that it is flat, or nearly so. In the language of physics, a flat universe implies that parallel lines never converge or diverge, and space may go on endlessly in all directions. Discussed in the previous chapter supports this view. If the universe expanded unimaginably fast in its infancy, then even a universe that started out with some curvature could appear flat to us today, just as a small patch of Earth's surface looks flat, even though the planet is round. This leads to the mind-bending idea that our observable universe is like a single tile in an endlessly sprawling mosaic. But what does it really mean for the universe to be infinite? In an infinite universe, there is no center, no edge, no final frontier where space stops and something else begins. It simply continues. Galaxies repeat, stars burn, and matter clusters again and again, without limit. If matter is evenly distributed, as cosmological principle suggests, then this infinity could contain infinite copies of galaxies, and perhaps even of you. Yes, one strange implication of an infinite cosmos is the concept of cosmic repetition. If the number of possible particle arrangements in a region is finite, and the universe is infinite, then patterns must eventually repeat somewhere far beyond the observable edge. There may exist a region nearly identical to our own, and beyond that, another with slight variations. This is not fiction. It follows logically from certain interpretations of modern physics. However, infinity is not something we can test directly. It's a mathematical construct, not a measurable quantity. We can never observe infinity. We can only infer it through indirect evidence. And because of this, the infinite universe hypothesis remains just that, a hypothesis. It sits at the intersection of science and philosophy, inviting awe but caution. There are also alternative possibilities. The universe could be finite, but unbounded like the surface of a sphere, which loops back on itself. In such a case, traveling far enough in one direction could, in theory, bring you back to your starting point. Space would be closed, but without edges. We'll explore this in more depth in a future chapter. Still, The idea of an infinite universe stirs something deep within us. It challenges our understanding of reality and forces us to rethink our place in the cosmos. What does it mean to exist in a universe without limits? Can our minds truly grasp such immensity? Perhaps the most humbling realization is this: if the universe is infinite, then everything we know, the Earth, the Milky Way, the cosmic web of galaxies, represents only an infinitesimal fraction of all that exists. The observable universe becomes not just a small piece of the whole, but a vanishingly tiny window into a boundless, eternal expanse, as we float within our visible bubble. We are reminded that the stars we see are but a few lanterns near the campfire beyond the horizon. If the infinite universe hypothesis holds true, lies an ocean of existence without shore. Chapter 4: Bubble Universes and the Multiverse Landscape. What if our entire universe, the vast collection of stars, galaxies, and cosmic structures we observe, was merely a single bubble floating in a grander, unfathomable sea? This is the central idea behind one of the most fascinating extensions of modern cosmology, the multiverse landscape, and the possibility of countless bubble universes beyond our own. This concept emerges naturally from the theory of eternal inflation, a powerful expansion of the inflation model discussed earlier. In this view, inflation doesn't end everywhere at once. Instead, different regions of space stop inflating at different times. When inflation ceases in a given region, a bubble-like universe forms, just like our own. But elsewhere, inflation continues, endlessly spawning new bubbles in a rapidly expanding background. Each bubble is isolated by vast, ever-growing stretches of space still undergoing inflation. These bubbles may never collide, never interact. They form a multiverse collection of self-contained universes, each one born from its own inflationary pocket. But here's where things become even more intriguing. These bubble universes might each possess different physical laws. The constants of nature, such as the strength of gravity or the masses of fundamental particles, could vary from one bubble to another. In some, stars might never form. In others, life, as we know it, might be impossible. In a few rare bubbles like ours, conditions might align just right for galaxies, chemistry, biology, and perhaps even consciousness to emerge. This idea is known as the multiverse landscape, a term borrowed from string theory, which proposes a vast number of possible configurations for the fundamental nature of reality. Each bubble might correspond to one of these configurations realized in a specific corner of the multiv. It's a dizzying notion. Instead of a single universe governed by a universal set of laws, we might live in a cosmic patchwork where reality takes on endless variations across countless domains. This view fundamentally shifts the way we think about science. If these other universes are causally disconnected, meaning no signal can pass between them, then they may forever lie beyond the realm of direct observation. Yet their existence might still leave traces. Some researchers have speculated that rare collisions between bubble universes could leave imprints on the cosmic microwave background, the afterglow of the Big Bang. While no definitive evidence has been found, the mere possibility invites both excitement and caution. There are also profound philosophical implications. If the multiverse is real, then the anthropic principle gains weight. Perhaps we observe this particular universe not because it's the only one, but because it's the one suited for observers like us. In an endless ensemble of bubbles, we find ourselves in the rare one that allows for thought, for wonder, for life. Still, the multiverse remains a frontier of speculation. It stretches our definitions of science, observation, and reality itself. Some scientists embrace it as a natural consequence of inflation and quantum physics. Others argue that ideas beyond empirical testability blur the line between science and metaphysics. Regardless, the bubble universe concept opens our minds to the possibility that what lies beyond the observable universe isn't just more of the same, but something fundamentally different. A reality where each bubble holds its own story, written in unique cosmic ink. We float in our own bubble of space-time, unaware of what lies just beyond the shimmering surface. And perhaps, scattered across the multiverse, other bubbles drift, silently containing their own stars, their own physics, and their own unknowable dreams. Chapter 5: The Cosmic Dark, Regions Without Light. When we gaze into the night sky, what we see is shaped entirely by light. Every star, every galaxy, every cosmic event we know of reaches us through photons, particles of light that have traveled across the depths of space. But what if there are regions of the universe that, although very real, emit no light at all? What if, beyond the observable edge, lies a cosmic dark, vast stretches of existence, silent and invisible? The observable universe is defined by the limit of light, how far it has had time to travel since the Big Bang. Yet beyond this luminous boundary, space may continue. It may be filled with galaxies that shine in wavelengths we'll never detect, or even with matter that never produced light in the first place. These dark regions may not be exotic in nature. They may simply be too far for their light to have ever reached us. Others may be dark for different reasons. they might contain mostly dark matter, which doesn't emit, absorb, or reflect light at all. Though dark matter makes up a significant portion of the mass of the universe, it interacts with regular matter only through gravity, making it invisible to telescopes. In some areas beyond our cosmic horizon, stars might have never formed. If local conditions weren't suitable for gas clouds to collapse, entire regions of space might be filled with cold, hydrogen and helium, silent, featureless, and eternally dark. These stretches would be indistinguishable to us from pure emptiness. Even more curious is the idea that some regions might contain objects older than light itself, relics from inflation or primordial structures too faint to be seen. Their very nature defies detection, but they could exert a gravitational pull, subtly shaping the fabric of nearby space. We might also consider dead galaxies long past their luminous lives. These galaxies may have formed stars billions of years ago, only to fade over cosmic time, leaving behind cold remnants, white dwarfs, neutron stars, and black holes. They would drift quietly in the darkness, invisible except through their gravitational influence. In truth, much of the universe is already dark. Even within our observable bubble, most of space is black. Light from distant galaxies is red-shifted by expansion, stretched into longer wavelengths. Eventually, this redshift renders light undetectable as it slips beyond the sensitivity of our instruments. This is known as the cosmic light horizon, and it acts as a second veil, further shrinking the volume we can meaningfully observe. The cosmic dark isn't just about what lies far away. It also touches upon what we can never see. Some structures might be hidden behind dense clouds of gas or obscured by black holes. Others might lie in dimensions beyond our perception, concealed not by distance, but by nature itself. And yet, even in darkness, the universe remains alive with structure and motion. Gravity weaves its invisible web. Matter clumps and evolves. Time marches on. Just because we can't see it doesn't mean it isn't there. To think of the cosmic dark is to acknowledge our limits. We are creatures of light, trying to understand a universe that is, by and large, hidden from our view. But in that darkness lies beauty. It reminds us that the cosmos is not constrained by what we can detect, and that mystery itself is part of the fabric of space, what lies beyond the observable universe may be not only unseen but unseeable, a quiet realm of potential waiting in stillness just beyond the reach of light. Chapter 6: Cosmic Topology. Is the universe folded or looping? When we imagine the universe extending beyond our field of vision, It's natural to picture it stretching infinitely in all directions, like an endless plane. But what if space is more complex than it appears? What if the universe, instead of being boundless and flat, is actually folded, looped, or shaped in ways that challenge our everyday intuition? This is the domain of cosmic topology, the study of the universe's global shape and structure. While cosmology deals with what the universe is made of and how it evolves, topology asks a deeper, subtler question: what is the universe's true form? At first glance, space appears flat, and observations of the cosmic microwave background support this. But flat doesn't necessarily mean infinite. In topology, a space can be flat, yet finite if it loops back on itself in a closed shape. Imagine the surface of a video game, where moving far enough in one direction eventually brings you back to where you started, not because you hit a wall, but because the space wraps around itself in 2 dimensions. This is easy to picture. A circle or a torus, the surface of a donut, are classic examples. In 3 dimensions, however, things get more abstract. The universe could be shaped like a 3 torusa higher dimensional equivalent of a donut, where each axis loops. In such a space, traveling in a straight line long enough might, in theory, bring you back to your starting point. One consequence of a looping universe is that light could travel in closed paths. If the cosmos is finite but wraps around, we might eventually see multiple images of the same galaxy coming from different directions and arriving at different times. Astronomers have searched the sky for these repeating patterns or ghost images, but so far, none have been found. Still, the absence of evidence is not conclusive. It could simply mean the loops are larger than our observable horizon. Another possibility is a universe with a more exotic topology, like a Poincare dodecahedral space, where space is stitched together in 12-faced symmetry. Such models, while speculative, offer a rich playground for understanding how space could be finite without boundaries, like the surface of a sphere, but in 3 dimensions. The implications of cosmic topology are profound. If the universe is finite and loops, it challenges our perception of infinity. It also raises the tantalizing possibility that we are living in a closed system with limits defined not by walls, but by curves in space-time. Yet even in such a universe, what lies beyond still becomes a meaningful question. Not in terms of space, perhaps, but in terms of structure, connection, causality. Topology may also intersect with quantum gravity, the quest to unify the laws of the very large and the very small. Some theories suggest that space itself may be composed of tiny, discrete loops or networks and that what we call geometry emerges from deeper, more abstract mathematical relations. Ultimately, our tools for measuring cosmic topology are still developing. As we refine our instruments and explore larger portions of the sky, we may find clues, patterns in the cosmic microwave background, distortions in gravitational lensing, or anomalies in galaxy distribution that point to a more intricate cosmic design. Until then, we are left with a beautiful uncertainty that space, far from being a simple canvas, may be a cosmic origami folded, curved, and wrapped in dimensions we are only beginning to explore. What lies beyond may not be more space, but a return loop, a fold, a path that brings us home, not by turning back, but by going forward. Chapter 7: Beyond Dimensions, Brains and Higher Realms. When we imagine what lies beyond the observable universe, we often think in terms of more galaxies, more stars, more space. But some theories suggest that beyond what we can see or even comprehend, there may exist entire realms of reality built not on familiar dimensions, but on hidden ones. These ideas emerge from cutting-edge physics, especially in the realm of string theory and its more expansive cousin, M-theory. At the heart of these theories lies a profound proposition that the universe we experience, with its 3 dimensions of space and 1 of time, may be only a slice of a much grander reality. In string theory, fundamental particles are not points, but tiny vibrating strings, and their vibrations determine the properties of matter. But for these strings to function as the theory requires, they must vibrate in a space of 10 or 11 dimensions, far more than we can perceive. Most of these extra dimensions, theorists believe, are compactified, curled up tightly on themselves at unimaginably small scales. They are all around us, but hidden like the threads in a finely woven fabric, too small for the eye to see. Yet their influence could be everywhere, shaping the laws of physics, the behavior of particles, and the structure of space itself. But some models go further. They suggest that while some dimensions are tiny and folded, others may be large or even infinitesimal only to certain kinds of entities or forces. In this framework, our universe could be a 3-dimensional membrane or brain floating in a higher dimensional space, often referred to as the bulk. All the matter and energy we know planets, stars, galaxies are confined to this brain. But gravity, being different from the other forces, might extend into the bulk. This opens the door to astonishing possibilities. There could be other brains, parallel to ours, each a separate universe with its own physics. Some might be close to us in the bulk, separated by only a microscopic distance in a higher dimension, yet forever disconnected from our own. Others might occasionally interact through gravitational effects or even catastrophic collisions. In some scenarios, the Big Bang itself was not the beginning of everything, but the result of two brains colliding in the higher dimensional bulk. The immense energy from such a clash could ignite a new universe our own while others form elsewhere. Under different conditions, these ideas are deeply speculative. And we have no direct evidence yet for extra dimensions or brains. But they offer elegant explanations for some puzzles of modern physics, like why gravity is so much weaker than the other fundamental forces. If gravity leaks into other dimensions, it would naturally appear weaker in ours. And so we arrive at an unsettling but beautiful idea that the true structure of reality might be far more layered and strange than we ever imagined. We may live on a floating surface in a multidimensional ocean, unaware of what lies just a breath away, other brains drifting silently, untouched, unseen, but very real. What lies beyond the observable universe may not be more of the same, but more of the differente, deeper architecture hidden by the very limits of our perception. In these higher realms, the universe becomes not just space, but structure. Not just motion, but vibration. Not just what we see, but everything we've yet to imagine. Chapter 8. The Heat Death, Horizon, Entropy, Beyond Sight, in the Grand Unfolding of Cosmic Time. There is a shadow that stretches toward the future. Slow, silent fate, governed not by explosion or collapse, but by entropy. This inevitable process, known as the heat death of the universe, paints a vision of a cosmos gradually slipping into stillness. But what if this quiet transformation is already taking place beyond our sight? What if parts of the universe have already crossed into this final state and we simply cannot see them? To understand this possibility, we must return to a central concept in thermodynamics, entropy. It is the measure of disorder, of randomness, of how energy spreads and becomes less useful over time. In isolated systems, entropy tends to increase, and the universe, as the ultimate isolated system, is no exception. As stars burn through their fuel, as galaxies collide and black holes devour matter, the universe slowly shifts from a dynamic, structured state into one of thermodynamic equilibrium, condition where no energy differences remain to drive processes or sustain life. In this distant future, all matter will decay, black holes will evaporate, and what remains will be a cold, dark sea of subatomic particles and radiation. This is the heat death scenario. But here is the truly mysterious part. The universe is already expanding faster than ever, driven by dark energy. Distant galaxies are moving away from us, and many have already passed beyond our cosmic event horizon, a limit beyond which we will never receive light or information from them again. For all practical purposes, these regions are lost to us, cut off forever by the acceleration of space. It's entirely possible that some of these unreachable regions are already deep into the path toward heat death. The stars may have burned out. The black holes may be all that remain. Entropy may reign, and no observers are left to witness the silence. To us, these regions appear as faint, red-shifted galaxies, or perhaps as blank patches of sky. But their fate is sealed in the cold logic of physics. Even within our observable universe, we are beginning to see the signs. Star formation has slowed. Galaxies are aging. The cosmic microwave background continues to cool. Time, like an ever-stretching river, carries everything toward equilibrium. But beyond the horizon, the transformation may be further along. There may be entire domains where the last light has already faded, where time moves without memory, and space is no longer a theater for drama. And we cannot know it not because it's hidden by dust or distance, but because it's beyond the reach of causality itself. This leads us to a haunting reflection. The limits of observation are also the limits of presence. Beyond a certain point, the universe is evolving in ways we will never witness. And that includes not just galaxies being born, but galaxies dying, slipping silently into the stillness of heat death. And yet, this is not a tale of despair. It is one of cosmic inevitability, of the graceful closure written into the laws of thermodynamics. It is a gentle reminder that all things change, and that even the universe so vast, so powerful, follows a quiet, natural rhythm. What lies beyond the observable universe may be a glimpse into our own future, a mirror stretched across distance and time, showing us not what once was, but what will be, a horizon not of light, but of entropisoft, invisible, and final. Chapter 9: Quantum Foam and the Edge of SPAC. At the most fundamental level, reality is a restless sea of uncertainty and fluctuation. Beneath the smooth fabric of space and time that we experience, physicists theorize a turbulent realm, known as quantum foam, bubbling, frothy landscape where the familiar rules of classical physics break down. Quantum foam emerges from the principles of quantum mechanics, which describe how particles and energy behave on the tiniest scales imaginable, the Planck length, roughly 1035, 1035, 1035 meters. At this scale, space itself is not continuous or smooth, but is jittering, fluctuating wildly due to the uncertainty principle. Space and time are thought to be in constant, fleeting turmoil, where tiny wormholes might open and close. And the very geometry of the universe is uncertain. This concept becomes particularly fascinating when we consider the edge of space-time, the cosmic horizon beyond which we cannot see. While the horizon is a macroscopic limit set by the speed of light and the age of the universe, it may also mark a boundary between the orderly cosmos we know and the frothy quantum realm beneath it. In this view, the space beyond the observable universe could be a wild, turbulent quantum landscape where space-time is so warped and unstable that the classical ideas of distance and time lose meaning. Some physicists suggest that the birth of the universe itself emerged from fluctuations in this quantum foma, spontaneous bubbling into existence. Moreover, the quantum foam could harbor tiny, ephemeral bridges known as quantum wormholes or Einstein-Rosen bridges, fleeting tunnels connecting disparate regions of space-time. While such wormholes are purely theoretical and would be extraordinarily unstable, they ignite the imagination about hidden connections beyond our cosmic horizon. The quantum nature of space-time also has profound implications for the information paradox and black hole physics. If space is fundamentally granular and dynamic at the smallest scales, then the classical idea of an event horizon, a point of no return, might be modified, potentially allowing information or energy to leak across boundaries thought to be absolute. This turbulent microcosm beneath the cosmic calm challenges the very nature of what it means to be beyond. It suggests that the universe's boundary is not a simple wall, but a seething, dynamic frontier where physics, as we know it, is replaced by something more complex and mysterious. In essence, the edge of the observable universe is not just a limit of distance. It could be a threshold into a quantum wilderness, a place where space and time themselves are uncertain and transient. As we ponder what lies beyond, we glimpse the delicate interplay between the vast and the minuscule, the cosmic and the quantum. The frontier is no longer a distant horizon, but a lively, bubbling realm at the foundation of all reality. Chapter 10: Echoes from Beyond. Gravitational clues. While light defines the limits of what we can see, there is another cosmic messenger that might carry whispers from beyond the observable universe. Gravitational waves. Unlike photons, gravitational waves are ripples in the fabric of space-time, itself disturbances caused by the acceleration of massive objects, such as merging black holes or neutron stars. They travel at the speed of light, but interact weakly with matter, allowing them to traverse the cosmos almost unimpeded. Since their first detection in 2015, gravitational waves have opened a new window to the universe. They provide a novel way to explore phenomena invisible to traditional telescopes, offering insights into the most violent and energetic events in the cosmos. But could they also carry messages from regions beyond our cosmic horizon? Theoretically, gravitational waves emitted in distant parts of the universe, even those currently beyond our observable limit, might someday reach us, because gravitational waves are less affected by intervening matter or cosmic expansion than light. They could reveal information about the universe's farthest reaches, or even hint at the presence of structures hidden. Moreover, some models of the early universe predict a background of primordial gravitational waves, faint, persistent ripples left over from the moments just after the Big Bang. Detecting these would offer a glimpse into the physics of inflation in the very birth of space-time, potentially illuminating conditions in parts of the cosmos forever inaccessible to light-based observation. In more speculative realms, gravitational waves might even carry signs of collisions between bubble universes in a multiverse. Such cataclysmic encounters could leave faint, characteristic imprints in the gravitational wave, background subtle disturbances, rippling through our own space-time from beyond our cosmic neighborhood. However, detecting these echoes is extraordinarily challenging. Gravitational waves are incredibly weak signals, requiring instruments of unparalleled sensitivity, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, and its successors. And while current technology is primarily focused on local cosmic events, future generations of detectors might broaden our reach, unveiling secrets from the universe's farthest frontiers. The potential of gravitational waves to reveal what lies beyond our observational limits is a testament to human ingenuity, new sense to perceive the universe not just by light, but by the trembling of space-time itself. As we listen carefully to these cosmic whispers, we may someday decode the faint echoes from beyond the observable universe, turning the unseen into the understood and extending our cosmic horizon beyond the veil of light. Chapter 11. The Great Silence. Why haven't we heard from there? One of the most profound mysteries tied to the universe, beyond what we can see, is the question of communication, or the lack thereof. If the cosmos is vast, perhaps infinite, and possibly filled with countless galaxies, stars, and planets, then why have we not detected any signs of intelligent life beyond our cosmic neighborhood? This profound question is often called the Great Silence or the Fermi Paradox. The observable universe, with its hundreds of billions of galaxies, seems to offer an enormous stage for life to arise. Yet, all our searches through radio signals, optical flashes, and other methods have come up empty. There are no confirmed messages, no beacons, no clear signs of civilizations reaching across the void. But when we think beyond the observable universe, this silence becomes even more profound, but also potentially to any signals or communication attempts. The cosmic speed limit, the speed of light sets a fundamental barrier. Even if extraterrestrial civilizations sent out powerful signals, those signals may never reach us if their origin is beyond our cosmic horizon. Moreover, the accelerated expansion of the universe, driven by dark energy, means that many distant galaxies are receding from us faster than light can bridge the gap. This cosmic recession creates causally disconnected regions, pockets of the universe that will forever remain isolated from each other. This isolation explains why, even if life flourishes somewhere beyond, their voices may never echo in our part of the cosmos. Additionally, civilizations themselves may be rare, short-lived, or uninterested in interstellar communication. They might use technologies beyond our detection capabilities or deliberately avoid broadcasting their presence to avoid unknown dangers. From a philosophical perspective, the silence invites reflection on our uniqueness and solitude in the vast cosmic sea. It also emphasizes the limits imposed by physics on what we can learn or receive from the universe beyond our reach. Yet, the great silence does not dampen human curiosity. Instead, it challenges us to refine our tools, expand our searches, and reconsider what it means to be alone nor not. The cosmos, the vast darkness beyond the observable universe, may be filled with wonders and beings unknown, but for now, their voices remain silent, locked behind the ultimate horizon, a reminder of the profound mysteries that lie beyond sight and sound. Chapter 12. The Observable Illusion. Are we in a cosmic bubble? Imagine for a moment that the universe we observe, the vast expanse of galaxies, stars, and cosmic phenomena, just a small bubble floating within a much larger reality. This idea challenges our most basic assumptions and raises a startling possibility. What if our entire observable universe is a localized region, a cosmic bubble, distinct from other such bubbles existing elsewhere? The notion of a cosmic bubble arises naturally from inflationary cosmology, where the universe undergoes rapid expansion in multiple regions, creating pocket universes, self-contained domains that may differ in their physical properties and conditions. You might reside in just one of these pockets, surrounded by an ocean of other universes beyond our perception. Within this bubble, we observe uniformity and familiar physical laws, but the boundary of the bubble marks a limit beyond which the fabric of reality could differ dramatically. This boundary is not a wall, but a horizon shaped by the dynamics of space and time. Some physicists propose that this bubble is the product of a phase transition in the early universe akin to bubbles forming in boiling water where different regions cooled differently, forming separate domains. Our bubble expanded and evolved, creating the cosmos we see today. If true, this implies that other bubbles, each with their own space and time, may exist beyond our horizon, forever unreachable. These bubbles may never interact with ours, making the question of their existence a profound scientific and philosophical challenge. From our vantage point, the cosmic bubble creates an illusion of completeness. We perceive our observable universe as all there is, when in fact it might be just a small island in a vast multiversal sea. This perspective reshapes our understanding of cosmic finitude and infinity. Our bubble may be finite, but the larger multiverse could be infinite and diverse. The observable horizon is not a boundary of the universe, but the edge of our cosmic bubble. Understanding whether we truly live inside such a bubble remains an open question. Scientists look for clues in the cosmic microwave background and large-scale structure of the universe, searching for subtle signs like patterns or anomalies that might betray the presence of a bubble boundary dot. In the meantime, the idea invites humility. We are residents of a special place, a cosmic bubble where conditions allow life, observation, and thought. But beyond lies a vast unknown of bubbles, other universes, other realities hidden just beyond the cosmic horizon. The cosmic bubble is both a limit and a gateway or frontier that defines what we can know and hints at the infinite possibilities beyond. Chapter 13. The Role of the Anthropic Principle. As we delve deeper into the mysteries that lie beyond the observable universe, we encounter a philosophical yet scientifically significant idea known as the anthropic principle. This principle explores a curious question. Why do the physical constants and conditions of our universe appear so precisely tuned to allow the existence of life, particularly intelligent life capable of observing the cosmos? At first glance, the fine-tuning of the universe may seem almost miraculous. Constants like the strength of gravity, the charge of the electron, or the cosmological constant are balanced within incredibly narrow margins. Even small variations in these values could render the universe inhospitable. No stars, no complex chemistry, no planets, and thus no life. The anthropic principle proposes that this apparent fine-tuning is not a coincidence, but a natural consequence of our presence as observers. In other words, we observe the universe to be compatible with life, because if it were not, we simply wouldn't be here to observe it. This is sometimes called the weak anthropic principle. In the context of what lies beyond the observable universe, this principle takes on a new dimension. If our universe is but one bubble among countless others in a vast multiverse, each with different physical laws and constants, then it's not surprising that we find ourselves in one where conditions are just right for life. Most other universes may be sterile and barren, but a few, like ours, provide a cradle for observers. This idea offers a potential explanation for the puzzling cosmological constant problem, where the energy density of empty space-dark energies observed to be tiny but positive. If the constant were much larger, the universe would expand too rapidly for galaxies to form. If much smaller, it might have collapsed. The anthropic principle suggests we find ourselves in a universe with a Goldilocks value simply because only such a universe allows observers. Some scientists extend this idea further with the strong anthropic principle, which suggests the universe must have properties that allow life to develop at some stage, implying a kind of inevitability or purpose. This interpretation borders on metaphysics and remains controversial. Yet it invites reflection on the relationship between consciousness and cosmos. The anthropic principle also influences how we interpret the search for extraterrestrial life and cosmic signals. The observable universe is just a small, hospitable bubble. The vast unseen cosmos beyond may be fundamentally different, mostly lifeless, or governed by physics incompatible with life as we know it. This notion, compelling, raises difficult questions. Does it imply a form of cosmic selection, where universes favorable to life are the only ones observed? Does it mean our universe is special, or just one of many possibilities? And how can we test such ideas when other universes lie beyond any possible observation? Despite these challenges, the anthropic principle remains a useful conceptual tool. It reminds us that our place in the cosmos is not arbitrary, and that the conditions necessary for life and for observation are intertwined with the very structure of reality as we gaze beyond the observable universe. The anthropic principle offers both an explanation and a challenge to understand not only what lies out there, but why we are here to wonder at it at all. Chapter 14: Cosmic Shadows, Dark Matter and Dark Energy Beyond the Horizon in the Vast Expanse of the Cosmos. Much of what shapes the universe remains invisible to us. About 85% of the matter in the universe is thought to be dark matter, elusive form of matter that neither emits nor absorbs light, detectable only through its gravitational effects. Even more mysterious is dark energy, a repulsive force driving the accelerated expansion of the universe, making up nearly 70% of the total cosmic energy budget. These two components together form the cosmic shadows that dominate the universe beyond the familiar stars and galaxies we observe. But what role do they play in the regions beyond the observable universe? And what might their presence or absence tell us about what lies beyond our cosmic horizon? Starting with dark matter, it acts as an unseen scaffold, guiding the formation and clustering of galaxies and galaxy clusters within our observable patch. Its gravitational pull shapes the cosmic web, the vast network of filaments and voids spanning billions of light years. But beyond the horizon, where galaxies fade from view, dark matter may continue its silent work, forming structures invisible to us. One intriguing question is whether the distribution and nature of dark matter are uniform throughout the larger universe, including beyond what we can see. Cosmological models generally assume a homogeneous distribution, but what if that assumption breaks down at scales larger than our horizon? Could there be regions where dark matter behaves differently, clumping more tightly, or perhaps even absent? Such variations could profoundly affect cosmic evolution. Without dark matter's gravitational pull, galaxy formation might be suppressed. Conversely, denser dark matter regions could host exotic structures or influence the growth of supermassive black holes, turning to dark energy. Its discovery in the late 1990s revolutionized cosmology. Dark energy acts as a mysterious form of energy intrinsic to space itself, pushing the universe apart with increasing speed. This acceleration means that many galaxies are moving away faster than light can traverse the expanding space between us, slipping beyond our observational reach. Forever beyond our horizon, dark energy's influence shapes the fate of those distant regions. It may cause entire swaths of the universe to become causally disconnected, never able to communicate with us or any other observers. These regions effectively become cosmic islands, adrift in a sea of expanding space. The nature of dark energy is still unknown. Is it a constant, unchanging property of space or something dynamic that evolves over time? Some theories propose that dark energy might vary across different cosmic domains, including those beyond our horizon. If true, it would imply a universe even more complex and diverse than imagined. Moreover, the interplay between dark matter and dark energy beyond the observable universe may give rise to phenomena We cannot yet predict variations in the large scale structure, the formation of unusual cosmic voids, or novel gravitational effects. Studying these cosmic shadows challenges astronomers and physicists to devise ingenious methods. Since we cannot directly observe beyond our horizon, we rely on indirect clues, the detailed mapping of cosmic microwave background radiation, gravitational lensing patterns, and the behavior of distant supernovae. As we learn more about dark matter and dark energy, we begin to appreciate that what lies beyond the observable universe is not empty space, but a vast and shadowy realm shaped by invisible forces, forces that govern the destiny of everything, seen and unseen. These cosmic shadows remind us of the limits of human perception and the grandeur of the unknown. They challenge us to keep exploring, to keep questioning, and to embrace the mystery of a universe far larger and stranger than our eyes can behold. Chapter 15: Cosmic Horizons and the Limits of Knowledge. As we peer ever farther into the cosmos, searching for answers about what lies beyond the observable universe, we confront an immutable truth. There are limits to what we can know. These limits arise not just from technological constraints, but from the fundamental nature of space, time, and causality. The universe has horizons, boundaries that define the edge of our knowledge and perception. The most familiar is the observable universe itself, defined by the maximum distance light has traveled since the Big Bang, roughly 13.8 billion years. But this is only a part of a larger picture. Because the universe is expanding, some regions of space recede faster than light can bridge the gap, placing them beyond our cosmic event horizon. This means that, even given infinite time, signals from these regions will never reach us. This cosmic horizon is more than just a physical boundary. It represents a profound epistemological limit. Beyond it lies a realm that, for all practical purposes, is forever inaccessible to observation, experiment, or communication. It is a frontier not of geography, but of knowledge. Yet the presence of horizons does not make the universe less real or less vast. Instead, it challenges us to refine what it means to understand the cosmos. We build models, test theories, and make inferences based on what we can see. But we must always remember that beyond the veil lies a domain where certainty dissolves. This has deep implications for cosmology and philosophy. Are the laws of physics we observe universal, or do they change beyond our horizon? Is the universe finite or infinite? Does causality hold unbroken, or do exotic phenomena beyond our reach disrupt it? The horizon also introduces a kind of cosmic humility. No matter how advanced our technology or how clever our theories, there will always be questions that remain out of reach. The limits of observation are inscribed into the fabric of space-time itself, but the human spirit resists limits. We use mathematical extrapolation, indirect evidence, and the power of imagination to peer past these horizons through theories like inflation, quantum gravity, and the multiverse. We attempt to sketch what may lie beyond. Even so, science accepts uncertainty as part of its process. The recognition of limits does not deter exploration, but enriches it. The edge of knowledge becomes a catalyst for discovery, driving us to find new ways of seeing and understanding. In the end, the cosmic horizons teach us that the universe is both knowable and mysterious, an eternal dance between light and shadow, between the seen and the unseen. What lies beyond the observable universe may forever elude direct experience, but it remains a powerful and compelling call to wonder, to question, and to dream. Chapter 16: The Fate of the Universe Beyond Observation. As we look out into the cosmos, charting the destinies of stars, galaxies, and clusters, we find ourselves contemplating the ultimate fate not just of the observable universe, but of all that lies beyond its horizon. The universe's vastness extends well past what we can see, and with it, the story of cosmic evolution continues, unfolding in ways both familiar and profoundly mysterious. Current observations suggest that the universe is expanding at an accelerating pace, driven by a mysterious component known as dark energy. This acceleration pushes galaxies ever farther apart, with many already receding beyond our cosmic horizon, destined to become permanently invisible. The implication is clear. The universe is becoming increasingly isolated, fragmenting into causal islands separated by expanding voids beyond our observable sphere. This fate likely plays out on grander scales. Regions of space once connected may drift apart forever beyond interaction. Star formation will slow and eventually cease, leaving behind relics white dwarfs, neutron stars, Atito, and black holes that slowly fade into darkness. One possible endgame is the heat-death scenario, where the universe approaches a state of maximum entropy. Energy differences smooth out, matter decays, and the cosmos becomes a cold, dark expanse, devoid of usable energy, a silent tomb for all structures. However, other fates are also theorized. The universe might eventually experience a big rip, where dark energies influence grows so strong that it tears apart galaxies, stars, planets, and eventually the very fabric of space-time itself. Alternatively, some speculate about a big crunch, a collapse of the cosmos back into a dense state. Though current data suggest this is less likely given the accelerating expansion beyond observation. These scenarios may already be unfolding, or may differ dramatically in other cosmic regions. If physical laws vary in the multiverse, some domains may end differently, some collapsing, others expanding forever, others cycling through endless rebirths. The interplay of quantum mechanics and gravity at cosmic scales might also introduce new physics that changes these destinies in unforeseen ways. The universe's fate might hinge on subtle effects still beyond our understanding, hidden in the realms beyond light's reach, in contemplating the fate beyond our horizon. We confront the ultimate questions about existence, time, and finality. What happens to matter and energy when the lights go out? Cosmic oblivion, absolute? Or could new structures, new universes emerge from the ashes? Though we cannot observe these distant futures directly, theoretical physics offers a canvas upon which these possibilities are sketched, each scenario reflecting profound truths about the nature of reality and the limits of human knowledge. As we ponder what lies beyond, we realize that the fate of the universe is not just a distant story, it is intimately connected to our own existence, our place in the cosmic tapestry, and the mystery of time itself. The universe beyond observation is vast, dynamic, and ultimately unknowable. Yet it beckons us to explore with mind and spirit, to embrace wonder in the face of uncertainty, and to accept that some questions may forever lie just beyond the horizon. Chapter 17: Parallel Universes and the Many Worlds. Interpretation. One of the most fascinating and mind-bending ideas about what lies beyond the observable universe comes from the realm of quantum physics, the possibility of parallel universes, also known as the many worlds interpretation. This concept suggests that our universe is not the only one, but just one branch in an immense, possibly infinite, multiversa, grand cosmic ensemble, where every possible outcome actually happens. The many worlds interpretation emerged from efforts to understand the perplexing behavior of quantum particles that can exist in multiple states at once, in a phenomenon known as superposition. According to this interpretation, whenever a quantum event with multiple possible outcomes occurs, the universe splits, creating distinct branches for each outcome. All branches are equally real, though isolated from one another. This means that beyond our observable universe, there could be countless parallel universes, worlds almost identical to ours, but with subtle or dramatic differences. In some, history unfolded just slightly differently. In others, laws of physics or constants might vary, and in still others, unimaginable realities could exist. These parallel universes are not separated by distance in space, but by their quantum state, different layers of reality superimposed yet separate. We cannot access or observe them directly, but their existence may explain puzzling quantum phenomena and the nature of reality itself. If true, the observable universe is just a tiny slice of a much larger quantum multiverse, with infinite possibilities unfolding simultaneously. This challenges classical ideas of determinism and uniqueness, suggesting that every choice, every random event, spawns new realities beyond the observable universe. These parallel universes may encompass realms where time flows differently, matter behaves unconventionally, or life follows alien paths. The very concept of beyond expands from physical distance to include multiple dimensions of existence. While the many worlds interpretation is elegant mathematically, it remains a subject of debate and lacks direct empirical evidence. Detecting or interacting with parallel universes, if even possible, is a formidable challenge. Yet, this idea opens profound philosophical questions. What does it mean to be here or now if countless versions of ourselves exist? How do free will and fate reconcile with an infinite branching cosmos? And what is the true nature of reality if it is a vast network of diverging paths? Exploring parallel universes shifts the focus from the cosmic horizon of space to the horizon of possibility, boundless frontier, where the universe is not one story, but many stories unfolding at once. As we contemplate what lies beyond the observable universe, the many worlds interpretation invites us to imagine a cosmos far richer and more complex than ever imagined. A cosmic symphony with infinite variations playing simultaneously beyond our sight. Chapter 18: Cosmic Inflation and the Eternal Universe. The story of what lies beyond the observable universe cannot be told without exploring the extraordinary. Theory of cosmic inflation, a brief period of exponential expansion that transformed the infant universe in its first fractions of a second. This rapid stretching smoothed and flattened the cosmos, setting the stage for the large-scale structures we see today, and perhaps hinting at a universe far grander than our immediate horizon reveals. Inflation theory, first proposed in the early 1980s, solves several puzzles of classical Big Bang cosmology. Why is the universe so uniform in temperature? Why is space flat rather than curved? Inflation answers these by positing that a tiny quantum-scale region expanded exponentially growing by many orders of magnitude in a tiny fraction of a second. But inflation has profound implications for what lies beyond the observable universe. The very nature of inflation suggests that this process may never truly end. Instead, inflation could be eternal, continuously spawning bubble universes within a vast multiverse. In this eternal inflation scenario, while inflation ends in some regions, forming universes like our own other regions continue inflating, creating an endless fractal of cosmic bubbles. Each bubble has its own physical properties and initial conditions, separated by vast inflating space. This means that our observable universe is just one of countless pocket universes existing in an infinite, ever-expanding cosmic foam beyond the horizon of what we can see. New universes, an eternal process of cosmic creation. The eternal inflation model also provides a natural context for the anthropic principle discussed in the previous chapter, explaining why physical constants appear finely tuned in our universe. We happen to live in one of the rare bubbles where conditions allow life. Yet, eternal inflation raises deep questions. If the multiverse is infinite and varied, how can we assign probabilities or predict outcomes? Does the process create duplicates of ourselves in other bubbles? And crucially, can we ever test these ideas, given that other bubbles lie forever beyond our cosmic horizon? Physicists continue to explore these questions through mathematical modeling, searching for subtle imprints of other bubbles in the cosmic microwave background or gravitational wave signals. So far, no conclusive evidence exists, but the possibility remains tantalizing. The eternal inflation transforms the concept of the universe from a singular event to an ongoing cosmic process. It paints a picture of a cosmos not with a beginning and end, but a perpetual sea of creation, where new universes bloom beyond our sight. This vision challenges our sense of uniqueness and invites us to see ourselves as part of an immense cosmic landscape, a single island in an endless ocean of universes. What lies beyond the observable universe, then, may be a never-ending process of birth and renewal, cosmic garden where space and time themselves continuously unfold in infinite variety. Chapter 19: The Mystery of Cosmic Voids. Amid the dazzling tapestry of stars, galaxies, and clusters that compose our observable universe, there exist vast dark regions known as cosmic voids. These immense expanses, often spanning hundreds of millions of light years, are strikingly empty places where few galaxies dwell and matter is thinly spread. Yet, these voids are not mere gaps. They hold profound clues about the structure and evolution of the universe, and perhaps about what lies beyond the edges of our cosmic horizon. Cosmic voids are the underexplored spaces between the filaments of the cosmic web, the large-scale structure of matter that weaves the universe together, formed by the gravitational pull of dark matter and the expansion of space. This web consists of dense clusters and long strands of galaxies separated by these enormous emptinesses. But why do voids exist? And what might their nature reveal about the universe beyond what we can see? One possibility is that voids are windows into the deeper cosmos. Their low-density environments may amplify subtle effects of dark energy and dark matter, helping cosmologists to test theories about the universe's composition and fate. By studying voids, scientists can refine their understanding of how matter and energy interact on the largest scales. Moreover, voids might extend beyond the observable universe. Regions beyond our horizon may contain enormous voids, possibly even more vast and empty than those we know. The distribution, size, and shape of these cosmic voids could vary significantly beyond our observational limits, hinting at a universe that is more inhomogeneous and complex than the smooth, uniform picture often assumed. Some researchers speculate that voids could harbor exotic phenomena as unusual gravitational effects or altered physics due to variations in dark energy or modifications to general relativity on large scales. Others imagine that cosmic voids might be the boundaries between different bubbles or domains in the multiverse, marking transitions in physical laws or constants. Intriguingly, the emptiness of voids may also have implications for the search for life. If voids are largely barren, they reinforce the idea that habitable zones and life-bearing galaxies cluster in denser regions, making our own cosmic neighborhood all the more precious. Studying cosmic voids is a challenge, requiring deep surveys and sophisticated simulations. Yet, these silent expanses are gradually revealing their secrets, offering a glimpse into the universe's vastness and the mysteries lying just beyond the observable edges. In contemplating the mystery of cosmic voids, we are reminded that absence can be as telling as presence. The great emptiness between galaxies speaks volumes about the forces shaping the cosmos and invites us to ponder what other vast, unseen structures lie beyond our sight. The cosmic voids stand as silent sentinels at the frontier of our knowledge, dark, vast, and full of possibility. Chapter 20. The ultimate question: why does the universe exist? As our journey through the cosmos draws to a close, we arrive at the most profound and timeless question of all. Why does the universe exist? This inquiry transcends science and ventures deep into philosophy, metaphysics, and the very essence of being. The observable universe with its countless stars, galaxies, and cosmic phenomena vast beyond imagination. Yet, all that we know is but a fraction of a grander reality stretching beyond our perception. Asking why the universe exists invites us to consider not only the cosmos's physical origins, but also the meaning and purpose behind its existence. From a scientific perspective, the question of existence begins with the Big Bang, the explosive event that birthed space and time roughly 13.8 billion years ago. But what caused the Big Bang? What existed before it, if such a notion even applies? Theories like quantum cosmology suggest that the universe might have emerged spontaneously from a quantum vacuum or from fluctuations in a primordial quantum foam. Random events without cause in the classical sense. Philosophers and theologians have grappled with this question for millennia. Some propose that the universe exists necessarily, that existence is a fundamental property of reality that requires no further explanation. Others suggest a purposeful creation, or that the universe is part of a multiverse ensemble where countless universes arise with varying properties. The anthropic principle, discussed earlier, hints that the universe is observed to exist in a form compatible with life because only such a universe allows observers like us. Yet, this does not fully answer the deeper why behind existence itself. Modern physics opens possibilities that challenge traditional ideas. Concepts like the holographic principle suggest the universe may be a projection of information, encoded on distant boundaries. Theories of quantum gravity and string theory hint at underlying structures from which space-time and matter emerge. Moreover, the idea that multiple universes coexist with different laws and constants reshapes the question, why does this particular universe exist with its specific properties? Perhaps it is one of countless variants, and our existence simply reflects a cosmic lottery. Ultimately, the question of why the universe exists may be beyond complete human understanding. It beckons us to accept mystery alongside knowledge, to embrace wonder alongside reason as we contemplate what lies beyond the observable universe. We realize that the quest for answers is as important as the answers themselves. The universe invites us to explore, to question, and to marvel at the profound mystery of existence in this grand cosmic journey. Perhaps the ultimate truth is that existence itself is a miracle, vast, unfolding story without end, where every question leads to new horizons, and every horizon beckons with mystery. What lies beyond the observable universe is not just a question of space or time, but a profound invitation to wonder at the very fact that there is something rather than nothing.